Alright, let's look into calorimetry. So, let's give a proper definition. So, here's Wikipedia definition. Calorimetry is the science or act of measuring changes in state variables of a body for the purpose of deriving the heat transfer associated with changes, blah, blah, blah. Calorimetry is the process of measuring the amount of heat released or absorbed during a chemical reaction. That's probably a better definition. It's the process of measuring the amount of heat released or absorbed during a chemical reaction. So by knowing the change in heat, it can be determined whether or not a reaction is exothermic or endothermic. But this is the main thing. So you might be aware that in chemistry, that chemical reactions sometimes involve the exchange of heat. For example, gasoline. Gasoline doesn't do anything by itself. However, if you add a little heat to it, it'll start reacting vigorously, generating more heat that fuels the reaction, causing it to continue to react in a chain reaction. As it reacts, it generates more heat. That heat causes more reaction to occur, which continues at an ever increasing rate. So in chemistry, some reactions require some starting energy to make it continue reacting. For example, you can have hydrogen, you can have oxygen in a room, and they stay as hydrogen gas, H2, and O2 gas. However, if you were to increase the energy, you can cause an H2 molecule to collide with an O2 molecule, and if it has enough energy, they'll react and form water, H2O. We would see a flame being produced. Can y'all put y'all's mask on? You would see a flame produced at the same time, and so it'll give off some heat too. So it requires heat to start, and it also gives off heat, which will cause more hydrogen gas to continue. But basically, this is the study of heat transfer. So, for example, burning a match, or system in this case will be the match, and the surroundings will be everything else. Initially, it has a ton of potential energy stored in the chemical bonds. If we were to add some energy, such as rubbing it and causing friction, friction adds thermal energy or heat energy into the match. It'll burn, and some of the energy will be released in the form of heat to the surroundings. So overall, we see that there is a loss of potential energy. You can no longer reignite it, and well, technically it would do that, but it loses some potential energy. It goes into the surroundings, and I just realized I don't ever think of this. Oh wait, no, it's doing it. So if we look at the total energy beforehand, we have energy in the surroundings and energy in the system. In this case, in this example, the energy of the reactants and products increases while the energy of the surroundings decreases. So we have some of the energy from the surroundings going into the system, causing the energy in the system to increase. However, total energy does not change. So would this be endothermic or exothermic? It would be endo because energy is going from the surroundings into the system. However, this is a more physics thing. The law of conservation of energy states that energy cannot be created or destroyed. It can only be transferred or transformed into other types of energy. So this is an endothermic reaction. We have some reactant and we add energy to it and we get some product. Note this is using reaction. Right now we're not really worried about reaction. We're going to only be worried about changes in temperature and phase changes. Start off easy before we get into actual equations. So here we have system at some energy. The energy of the system has decreased. So in this example, the energy of the reactants and products decreases while the energy of the surroundings increase. Again, the total energy doesn't change. So this would be an exothermic reaction. In an exothermic reaction, usually we have the reactant break apart into some other product and form and release some energy. I really don't like this PowerPoint, but it's the PowerPoint I used last year and the year before. Yeah. Don't have to write this down. I would write this instead. The direction of heat flow. It always heat always flows from hot to cold. So in the case of melting, heat would be flowing into the system. In the case of freezing, heat would be leaving the system. Again, I would just write heat always flows from hot to cold. This is too technical. I don't like this. Heat always flows from hot to cold. You might have heard of a calorie. It's the something what we use, like for example, food uses calories. It's the amount of energy that is released in it. Uh, so there are 2 calories. You really just need to put this bottom number. 1,000 calories equals 1 calorie. Do y'all notice the difference between the 2 calories? One is capitalized. The capitalized calorie is called a food calorie. Lowercase calorie is called a scientific calorie. The food industry thought it would be too hard for people to read 4,000 calories and too big of numbers, so they just divided everything by 1,000. They should have been calling it kilocalories, but they thought kilo would confuse people, so they left that off. Then it's probably referring still to a kilo food calorie. Its food industry is very, yes. We won't really be using calories in this class. If we do use calories, just bless you. We'll be using joules. 1 calorie is equal to 1 scientific calorie is equal to 4.184 joules. So 1 calorie is equal to 4.184 joules. That's the conversion factor. One food calorie is equal to 4,184 joules. Just multiply both sides by 1,000. And then convert the left side to food. So 1 food calorie with a capital C is 4,184. I'll tell you what to write. This is a very scientific device. It is 2 coffee cups with a lid with a hole cut and a thermometer through it. Believe it or not, this is actually very good. Styrofoam is a very good insulator and can prevent heat from escaping it very well. To even make it better, they double it up. But this is known as a coffee cup calorimeter. Basically, if you want to do a reaction, which my thermometer should be coming in tomorrow, my digital one, that's more accurate than these thermometers. We'll be making this. Unfortunately, I don't have any styrofoam lids to really insulate it too well. But basically, whenever you want to do calorimetry, you need to prevent the heat from escaping to the environment. You want to, whenever you try to figure out how much heat is lost or gained, you really want it to be in an enclosed, isolated system. I think y'all can stop taking notes, as this is just other types of systems. So we definitely won't be using a bomb calorimeter. We will be using the coffee cup. It's simple to make, and actually works very well. Yeah, so they like to they produce a lot of heat really quickly to and control to heat things up. If you're curious about how they actually measure the calories in food, they actually put it into substances, heat it up, and see how much energy was used in vaporizing it. So, heating curves. We should all be familiar with heating curves. So, during the solid phase, when we're heating it up, only the kinetic energy is increasing. During the melting phase, it switches to where we're increasing the potential energy. During the liquid phase, kinetic energy is the only thing increasing. During the boiling, only potential energy is increasing. During the gas, only the kinetic energy. So you can write this down again. Temperature change is a change in kinetic energy or molecular motion. It depends on something called heat capacity. In this class, we're going to be off slightly from the SI units. We're going to be dealing with grams and not kilograms. So a kilogram of water weighs 2.2 pounds. We aren't going to be dealing with 2.2 pounds of water. We're going to be dealing with grams. Your water bottle is half a kilogram or 500 grams of water when you first get it. We'll be more dealing with things less than 1 gram. So heat capacity is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. You'll see this definition. Sometimes this will be called specific heat. So I put parentheses around this and say specific heat. You'll sometimes see the definition be 1 kilogram by 1 Kelvin. Do y'all remember what I said about Kelvin and degree Celsius? They're the same if we're referring to changes in temperature. But in this class, we'll be dealing with grams and not kilograms. You'll notice when we go into these specific heats or heat capacities of different chemicals, water has an unusually high specific heat or heat capacity. It's actually this reason why life actually exists is because of water. Water has some very unique properties to it. Without water covering most of the surface of the world, we would have temperature changes that would probably fluctuate between negative 200 degrees up to like 300 degrees during the day. Water helps keep the temperature very consistent because water requires a lot of energy to heat up. So during a phase change, it's a change in potential energy or the molecular arrangement. During a phase change, temperature remains constant. This means kinetic energy stays constant. And then we introduce heat of fusion. I don't use this delta H fusion symbol. I just do HF. But I don't put the US on it. I don't put the delta. But heat of fusion is the energy required to melt 1 gram of substance at its melting point. We also use the same word to describe freezing. The energy released while freezing 1 gram of a substance at its freezing point, which is the same as melting point. We also have heat of vaporization. The energy required to boil 1 gram of a substance at its boiling point. It's usually larger than heat of fusion. Would anyone like to guess why? Why would, though, it be easier to melt something than boil something? So, let's say you're standing still. How easy would it be to increase your speed by 5 miles an hour? To go from 0 to 5 miles an hour. Now imagine you're running at 20 miles an hour. How easy will it be to increase your speed from 20 to 25? I think at one point the world record was around 22 miles an hour. Usain Bolt, I think, can run at a top speed of 26, 28. In order to get those particles into a higher energy state, they're already at higher energy state. In order to continue and bump them up even higher requires more energy. So when you have very little energy, it's easy to add some energy to it. But once you already have a lot of energy, it's hard to keep adding energy to it. So sweating, steam burning, there's a physics toy called the drinking bird that moves based on this. But we can see if you were to plot the entire time. So, for example, think about when you're boiling water. When we started out with ice, we didn't have to wait that very long for the ice to fully melt. However, if we were to sat there and try to wait for all the time for it to fully boil, we'd be there for like an hour or two, right? Because to convert all the liquid into gas would take a significant amount of time. Again, these two units intermatch. We won't be doing phase diagrams again. It throws in a joke. Small piece of ice which lives in a test tube fell in love with a Bunsen burner. Bunsen, my flame, I melt whenever I see you, said the ice. Bunsen burner replied, it's just a phase you're going through. So, let's look at actually solving this mathematically. This is actually the reason why I use this PowerPoint. It's the only one that actually shows the image of it. So let's say we're warming up some ice. The ice started at negative 80 degrees, going up to 0. Calculate the heat. Let me stop before going over this and write this down. I already went over delta, right? Did I? The Latin alphabet? Greek alphabet? So, delta T, this is change in. Capital T stands for temperature. And it's pronounced delta T. The Greek letter delta is just a triangle. It's a equilateral triangle. Not quite an equilateral. So heat is equal to mass times the change in temperature times capital C. So this is heat. It'll be measured in joules. This is mass. In this class, we're going to be using grams. In my other classes, we use kilograms. This will be change in temperature. It could be degrees Celsius or Kelvin. This is a change. And this is usually called specific heat or heat capacity. I prefer the term specific heat over heat capacity. And this can be measured in joules per gram degree Celsius or joule per gram Kelvin. Note, only used during a single phase when temperature is changing. We also have heat diffusion. Again, it's a heat, so it's measured in joules. Sometimes I might use QF to keep it consistent with the Q up there. Because for normal heat, they use a Q. This is just mass times I'm actually going to just use a Q. Sorry, erase this. I'm trying to be consistent without confusing. So heat is equal to mass, because this PowerPoint is different. HF. So this is heat. Heat of fusion can mean two things. It can either mean the total heat or this constant. I like it, so that leads to confusion, because you can call this the heat of fusion and this the total heat of fusion. I try to eliminate that. We have mass and grams. And then we have the heat of fusion. You might say specific heat of fusion. This would be measured in joules per gram. Used during melting or freezing. So positive during melting, negative during freezing. I will also say here, this Q is positive if heat is gained / added, and Q is negative if heat is lost or released. And then we have Q equals mass times heat of vaporization. Heat of vaporization constant would probably be a better word here. Still joules per gram. Used during vaporization, boiling, or boiling, or condensing, the reverse. It'll be positive. Heat is positive when boiling. Negative when condensing. In addition to all this, there's also molar specific heat, in which case, instead of lowercase m for mass, we use capital M for moles. I tend to not try to confuse y'all and use both systems. We'll stick to measuring everything in grams. If you're given moles, just convert moles into grams. They use different values here. They use CP for for the first equation, which is what I do here. For ice, the CP of ice is 2.077 is what they use in PowerPoint. Any table you find is oddly enough going to have different values. I will give you the values of all these substances, and you just use whatever values on the table. This value, we treat it as a constant, but it depends on pressure and temperature. So during this phase, and when we're adding heat to ice and warming it up, when we're adding heat to it, you can figure out how much heat is added by using this equation. When it starts melting, we're still adding heat, and we can use heat of fusion equation. Note they use C instead of H. For water's heat of fusion or specific heat of fusion, they use 333. For the temperature phases, it's always going to be this equation, except for we'd use a different CP value. We'd use the CP for when water is liquid. So CP, again, also depends not only on mass and temperature, we'll assume it's constant though, but it depends on the phase too. But I would copy this down and we'll do an example. There I go, copy it down. Okay. So, how much, and I'll tell you the values, we'll use the values on this. We begin by using a table. So we have ice, CP equals 2.077 joules per gram degree Celsius. Water, CP is equal to 4.184 joules per gram degree Celsius. And steam, CP is equal to 1.87 joules per gram Celsius. Heat of fusion, or HF, is 333 joules per gram. And heat of vaporization is 2,256 joules per gram. We'll assume these are constant, and this is for H2O. How much heat is required to heat negative 10 degrees Celsius ice cube with a mass of 50 grams to 20 degrees Celsius water? So how much heat is required to heat negative 10 degrees Celsius ice with a mass of 50 grams to 20 degrees Celsius water? I like drawing a little scale to help keep me in track with all the equations that will be involved in doing this. So we start out with negative 10 degrees Celsius ice. And we're going to be heating it up. So it's a solid during this portion. That's all right. Solid in here. Here at 0 degrees Celsius, it will melt. And then it'll become a liquid and heat up to 20 degrees Celsius. So first we need to start out with negative 10 degrees Celsius ice and go to 20 degrees Celsius water. For every point as we're going from this line up to this line, we have to account for the different phases and phase changes. During this portion, when it's just a solid, so we're going from solid negative 10 degrees Celsius ice to solid 0 degrees Celsius ice. From there, so once we go up to here, we're then going to convert between negative 0 degrees Celsius ice to 0 degrees Celsius water. This would be the melting phase. From there, we're going to increase from 0 degrees Celsius water to 20 degrees Celsius water. What we end up with is 3 equations. When we're in a single phase, we will do that Q would equal mass times change in temperature times the CP for this phase. So remember that delta T is final minus initial. So 0 minus negative 10. So 0 minus a negative 10 is a positive 10 degrees Celsius. So our mass is 50 grams, 10 degrees Celsius. And for solid ice, we come up to solid or CP is 2.077 joules per gram degree Celsius. So in order to heat ice from -10 to 0 requires 1038.5 joules. Now to melt ice to water, there's no temperature change. We would use Q is equal to mass times the heat of fusion value. So 50 grams times heat of fusion is 333 joules per gram. Grams cancel out, giving us just joules. 16,650 joules. So it requires 16,650 joules just during the melting phase. Then to heat water from 0 to 20 degrees Celsius, we would go back and use this equation, but we change which CP value we use. So it's 50 grams. We're going from 0 to 20, so 20 minus 0 is 20 degrees Celsius. Let's be 50. And the CP for liquid water is 4.184 joules per gram degree Celsius. Which equals 4,184 joules. So the total heat would be equal to the sum of all three of these. So it'd be 1,038.5 joules plus 16,650 joules plus 4,184 joules. And we get total heat required 21,872.5 joules. This is why it took so long for the ice to fully melt. Most of the heat was going into melting the ice, not during the two phases of increasing its temperature. Anyone confused? We're going to do multiple examples of this. Yes, today and tomorrow. Well, mostly tomorrow. Again, this is best learned by practice. Working on this. So basically, we're going to use these equations, and we just need to look at what values to use. Yes. The most difficult thing is you have to. So if you were to look at the difference between -10 and 20, that's a total of, it jumped 30 degrees. However, we can't plug that into this equation because during some portion it was solid and during another portion it was liquid. The specific heat has changed. So the specific heat of ice is different than the specific heat of water. It's actually easier to melt ice than it is to warm up water. It would take twice as long to heat up water than it would be to heat up ice. So you're going to have to break it up into different segments. So yeah, I got like 3 minutes. So for example, if we were going to go from solid, let's say -10 degrees Celsius, At 0 degrees Celsius, it's going to melt. And then up here at 100 degrees Celsius, it's going to start boiling. And it'll be solid in the middle. And then it'll eventually reach like 120 degrees Celsius. And so this will be when it's a gas. I'm trying to think how I drew this last year. I think how I did it was I put melt on the side. Ah, yeah. But every time you run, so you could only do an equation. So you need to do equation per block and equation for every divider. Yes. So what you started with, adding heat and going up to some temperature. So we'll need to use Q equals M delta T Cp for whenever there's a change in temperature during a single phase. And during the phase changes of boiling, we'll need to use Q equals MHF for HV and Q equals MHF. So for doing this, there'll be five equations you have to add up in order to get the final answer. It is going to be a lot of math, but I think once we work with several examples together, it'll make more sense. It's going to get more complicated. Wait until I start doing two things, like we're putting ice and water, and you're now going in two directions on this plot. By the way, the code word. There's the code word of the day.